Hardness is a measure of polyvalent cations in water. Polyvalent cations are ions with a charge greater than +1. Hardness generally represents the concentration of calcium and magnesium ions because these are the most common polyvalent cations. Other ions, such as iron and manganese, may also contribute to the hardness of water, but are generally present in much lower concentrations. Waters with high hardness values are referred to as hard, while those with low hardness values are soft. Stream water hardness reflects the geology of the catchment area. Hardness is a reflection of the amount of calcium and magnesium entering the stream through the weathering of rock such as limestone. When limestone is weathered, it dissolves into calcium and carbonate. Calcium is an important nutrient that is used by plants and animals. Carbonate buffers the stream's pH. In addition, hardness mitigates metals toxicity because calcium and magnesium help keep fish from absorbing metals such as lead, arsenic, and cadmium into their bloodstream through their gills. The greater the hardness, the harder it is for toxic metals to be absorbed through the gills. Sometimes hardness also provides a measure of the influence of human activity in the area. For instance, acid mine drainage often results in the release of iron into a stream. The iron produces extraordinarily high hardness readings. For these reasons, hardness is a useful water quality indicator. Hardness also has domestic effects. The amount of soap that is needed to produce foam or lather is directly related to hardness. Hard water requires more soap because the calcium and magnesium ions form complexes with the soap, preventing the soap from sudsing. Hard water can also leave a film on hair, fabrics, and glassware. Hardness of water is very important in industrial uses also. This is because it forms scales in heat exchange equipment, boilers, and pipelines. Some hardness is necessary in plumbing systems to prevent corrosion of pipes. Correct water sampling technique is important to reduce the amount of error involved in the sample collection process and to accurately depict what is occurring in a stream setting. To correctly collect a sample from a stream, the individual should find a fairly deep, representative area near the center of the stream's cross-section. This is often done at the thalweg, which is a stream's deepest point in its cross-section. Once there, they will use a standard bottle for the sampling. At this point, the individual should invert the bottle upstream of their body and fill the bottle partially and rinse it 3 times. It is important to always sample upstream to minimize the effect you are having on the water quality. While this may not be as important for hardness, to get other stream measurements such as total suspended solids, any disturbance will alter the sample and result in an unrealistic depiction of the stream's conditions. After rinsing, the bottle should be submerged a 4th and final time in an upside-down manner, approximately 1/3 depth into the water column to collect the water sample. At each sampling site, it is important to take multiple samples at the same time to use as a composite. This helps to get a more accurate depiction of current conditions and helps to further minimize sampling error. In deeper streams or rivers, it is possible to use a device to help you get a sample from an otherwise inaccessible location. Whether collected by hand or with a device, the sample collection procedures should be followed. Your job is to determine whether water samples collected from 5 different sampling sites are soft or hard. From the determination of the hardness of each of the samples, it should give us some idea about the underlying geology. If the water samples are hard, it is likely the underlying geology is limestone. Conversely, the softer the water, the greater the likelihood that the underlying geology is sandstone. So, take a look at the 5 sampling locations and help us determine whether the samples are hard or soft so we can learn about the stream's underlying geology.